She was great too. She was the most unassuming person you would ever know. She treated everybody as equals, like in a way that I've never seen anybody else do. Like, she was the kind of person who, like, she's super happy to talk to you and just like chat, and then she would like go to some political rally, and like after the governor had spoke, she'd like go up to the governor because she didn't want to talk to him about a few things, and it didn't faze her one bit. You know, she was fantastic. Okay, let's talk business. The lab 3 is due this Friday. We're working on clarifying the spec. I think there's some questions about it. Has anybody looked at it? Gotten started? Okay, a couple of you. Any questions we can resolve quickly today? Otherwise, we'll probably discuss this more on Wednesday once you've actually looked at it. Okay, no burning questions, great. Then I also wanted to talk just a little bit about final projects. So in this class, 20% of your grade is final project. And I wanted to ask you about an experiment that I wanted to do. So let me tell you the way it normally works. In normal graduate level CS class, many of them have a final project in lieu of a final exam. You do something research-ish that you're interested in, you write up a big report, you spend a bunch of time on it, you turn it in, I grade it, and like that's the grade of your final exam. The problem with that is it's very subjective. People do very different kinds of things. So I was talking to a colleague, is Brent Adams. He runs the animation department, and so the animation people, their entire thing for like a year, they have one assignment. Actually, they have 3 assignments, he said. Assignment number 1, make a film. That's their assignment. Assignment number 2, email me your grade at the end of semester 1. Assignment number 3, email me your grade at the end of semester number 2. Those are the 3 assignments. And he says he does that. So he's gotten into a lot of trouble for this. But apparently it works really well. And he says what this does is it decouples the fear of failure from the ability to be creative. So students don't have to worry about what Brent Adams wants in a film. They just like go and make the best film they can. He says it's very motivating for them. So I thought, and I was really inspired by this. I thought, how can I do the same thing for you guys? I want you to do a final project that's awesome. I want you to take risks. I want you to experiment. I want you to swing for the fences. And if you miss, I want that to be okay somehow. But I still want you to put some real effort into it. So I thought, okay, here's the experiment that I have in mind. If your grade is supposed to be 20% of your overall grade, and you're supposed to spend like 10 hours a week or something in this class, there's like 160 hours worth of effort roughly that is expected. And so I thought, well, 20% of that would be roughly 35 hours, maybe 40. I thought, well, what if I do this? For your final project, you pick whatever you want. It's some awesome machine learning problem that involves deep learning. And your grade is based entirely on the number of hours that you spend on it. So if you want an A, you spend 35 to 40 hours. If you want a B, you spend 30 hours. You want a C, you spend 20 hours. And there's just a couple of, the rules would be something like you can't read for more than like 4 hours, and you can't like clean your data for more than 20. So like at least half it has to be actual learning, right? But besides that, it can be whatever you want. And I thought this would have the advantage of decoupling, and then you could really try something great. And if you failed, that would be okay. I mean, like, because deep learning, you'll find, like, you're going to try really, really hard, and sometimes, like, your net just won't learn. And I want there to be a safety net for you for your final project, if that's the case. Like, I'd much rather have you try something ambitious and not succeed than try something dumb and small and succeed. Okay? So there's some disadvantages to this, obviously. I think if you want to, you could game the system. You could probably find 40 hours worth of stuff to do that's unproductive. But I'm hopeful that those of you that care deeply about deep learning would see this as an opportunity to do something good. I've never heard of anybody doing anything like this before, though, so I thought I would ask you, does this seem like a good idea?
Yes.
Okay, go ahead.
One thing I'm worried about is that we have projects every week up until the final project.
Yeah, so what you should not do, for various reasons, is wait until the week before it's due and then start. And so what I'm going to try to do is give you some sub-assignments throughout the semester, and you'll like submit a little proposal to me or something. It won't even be graded, just like something you have to check off. Or maybe if you don't do it, I'll dock you points or something. Because what I want you to do is spread that 40 hours across the semester. Part of the practical reason for that, by the way, and the practical reason to not wait until the last minute is because it takes like hours and hours and hours to train neural nets as you're beginning to learn. And as they get bigger, you'll find that only gets worse. And so if you wait till the last minute, it may very well be that you just don't have enough wall clock time to like train your net. And training time doesn't count on the 40 hours. Any other thoughts, reactions? Go ahead.
So what if some of us are in the same research group and have a large set of data that we want to use, but there's like, say, 3 of us?
That's cool.
Could we all work on that
So the parameters, yeah, so the parameters of the final project are, you do whatever you want. You use whatever code you want. Google anything, GitHub, whatever repo, totally fine. Frameworks, existing code, totally fine. Except that you have to do something sort of in addition to whatever you've got. So like if you download some awesome toolkit, you have to do something in addition to using the toolkit, if that makes sense. You're totally welcome to use whatever data sets you want, so you can share data, that's totally fine. Yeah, go ahead.
What about like your group project? Is that out of the question?
Group projects are okay. So I think this format would let you guys all work on a group project. And I wouldn't have to assess whether or not your group project was exactly 2 times the effort of one group project. I think this also removes an element of subjectivity that I've seen before, because now I don't have to compare XYZ project to ABC project subjectively and say, oh, that's clearly an A and that's clearly a B. What I'll probably do is I will ask you for a little write-up about your project in addition to the hours. And then I may tweak the grading scheme just a little bit to, like maybe it'll be 80% based on hours and 20% based on a little write-up or something like that. I want the majority of the grade to be based on your effort, not necessarily your results. Go ahead.
I love this idea because it evens the playing field is another advantage a little bit where this is kind of a multidisciplinary class. So a lot of CSR may have more experience, but I think that would you be expecting like an allocation of time as well?
Yes. So what I'll ask you to produce is a log, like just like a spreadsheet. It says on this date, this many hours, this date, this many hours, and I'll just like sum them up and multiply by 300 or whatever, and that'll be your grade. Okay. Yeah.
So for a religion class I'm taking, it's actually the final project for that class is basically the same format. There's no, you just have to produce something like meaningful at the end, and you have to put in a certain number of hours, and it can be pretty much anything. So I actually decided, I just submitted my proposal, hopefully it gets accepted, to do a deep learning analysis on like Joseph Smith's writings. It's for Foundations Restoration. Would it be possible to like do both of the projects together to double dip, or is that not kosher? Because I'm already going to be putting in at least 12 hours into that, so it would be nice to be able to work on them together.
In general, double dipping is not.
Okay.
Yeah. We don't usually like that in any form. So I think you should, whatever you do for this class should be independent of whatever you do for that. I mean, maybe you could do some deep learning project on ancient religious texts or something. But I would want you to spend your dedicated 35 to 40 hours on this project, and then in addition to the 12 on that. Cool. Yeah, go ahead.
So the objective is the actual deep learning and not necessarily like the data where we're getting it, or so could we do like a Kaggle competition or something like that?
Totally, but so, and I'll explain this more in detail later, but what I don't want you to do is like download a data set from Kaggle, download some GitHub repo, point the GitHub, whatever code, at the Kaggle data set, and then like send me a PDF of the result. Like what I will explain this later, but what I want you to do is pretend you're a data scientist. I want you to take a model, take a data set, try it, probably won't work, and then start iterating. Do this test, report on the result. Do this test, try that. Reinitialize this, try a different topology. Clean your data set in a different way. And I want to see that process of sciencing the data.
Creating your own model. You can transfer from others
and stuff
like that.
Yeah, that's totally fine. But wherever you start, I just expect effort beyond that.
Have you ever seen any publications come out of Type 1 projects?
Yeah, totally. Yeah, it's a great chance to try to do something awesome. Okay, one more question, we gotta move on.
So just one of my kind of fears is that there's a lot of material in the class that we just won't cover until we get closer to the end. Right?
Totally.
So in that case, we just kind of go for it and see what happens. And
Yeah.
something the last week that really helps us. And
Yep.
okay, great.
Yep. That's right. Okay, if you have other thoughts or concerns or questions about this, let me know offline. We'll probably talk about it more as we go on. Okay, any other burning questions at this point? Okay, great. So let's move on then. So last time we began our discussion of convolutions, and today we're going to wrap that up. We're also going to talk about getting things to work. But I had a good conversation with some students at the end of class last time on Friday, and I thought maybe just a brief summary of a few things would help clarify kind of where we've been and where we're going. So we started off with this idea that we are interested in various tasks that can be framed as functions. We've got some input, doing some output. We've got these powerful things which we're calling deep neural networks that are function approximators. We started off with a very simple function that was the linear classifier. So we have a model and some input, in this case image, and some weights, which we're going to learn eventually. But the form of the model is you take the image and we're going to reshape it to be 32 times 32 times 3 by 1. So turn it to a vector. And then dot is multiply. So we're going to multiply this vector, which is now long and skinny, with this W matrix, and we're going to get the scores. And then that'll be plugged into some loss function down the way. This is like the essence of our model, right? Okay, so this is a linear model. And we think of W, when it's learned, we think it's sort of extracting some features, or maybe in this case, once it was learned, it would be like eigencast. Because this is our very first model. And then we quickly tried this model. So this model was a slightly more complicated version, but what did we decide was wrong with this model? So take a look at it.
It just collapses.
Okay, yeah, this is the linear collapse model, right? We take X, we reshape it to a vector, we multiply it by a matrix, we get some hidden layer. We take that hidden layer, multiply it by a matrix, we get some new hidden layer, and then we take that, multiply it by a matrix, and get some scores out. And we decided that doesn't work because it's still linear, but we can sort of think of this as a 3-layer neural net that just doesn't happen to work very well, or any better than a 1-layer neural net. So what we decided was we needed some nonlinearities. So then we decided maybe we'd have some biases. So we decided to do something like this. So we start off with an image, we reshape it, and that gives us a flat vector. We take it, we multiply it by some matrix, and we add a bias. And that gives us our hidden layer, but then we take that hidden layer and we pass it through some nonlinearity, like a ReLU. And then we take that, dot product it, add a bias, that gives us this, which we pass through a ReLU, that gives us H2B. Then we take that, multiply it, add a bias, and that'll be our scores at the end. Okay, so how many layers does it have? So we've got, I mean, it depends on how you count, right? But so we've got 2 hidden layers in the middle. So what are some advantages and disadvantages of this model we've talked about so far? Any thoughts? Yeah?
Well, it's nonlinear.
Nonlinear.
Progress.
Okay, so this is a nonlinear function. Okay, go ahead.
The hidden layers make it so that we don't understand exactly what's happening in the middle there.
So uninterpretable hidden layers. No idea what's going on. Yep. Yeah.
The value is not zero-centered, so.
Okay, so some questions about, is this the best nonlinearity? Yep, good.
Going beyond 1 layer allows us to solve more complex problems like the exclusive OR.
Yeah, so this is now some just crazy nonlinear something or other. Very difficult to characterize as the sort of decision surfaces that this thing is capable of, although we know it's piecewise linear. But yeah, we can now capture the complexities and nuances of more complicated data sets. Yeah?
Without convolutions, this kind of model might explode the number of parameters.
Okay, parameters. Yeah, let's talk about parameters for a second. So how big is W1? Well, we don't really know because we don't know how big H1 is, but let's suppose H1 is some big-ish number, like 1,000. So how big would W1 be? Yeah, so it's 32 by 32 by 3 by 1,000, which is, what's 32 times 32 times 3? 2,700, something like that? 2,000? Okay, so that's like, so 2,700 times 1,000, what's that? 2.7 million. So there's 2.7 million parameters just in that W1, if H1 is 1,000. And then, if suppose H2 was 1,000, how big would W2 be? 1,000 by 1,000, so another million. And then scores is 10, so W3 would be like 1,000 by 10. So parameters add up very, very quickly if we're just doing, these are called fully connected layers. By the way, why are they called fully connected?
Because every input's connected.
Yeah, so every element of the H1 vector could potentially depend on every element of X flat. Okay, so it's fully connected. Okay, but we decided this maybe wasn't the best thing, and we moved just a little bit further, and we said, okay, let's instead of doing fully connected layers, let's do convolutions. So now we notice that we don't flatten X to begin with. Why not?
Now, there's a structure.
Yeah, we're preserving the tensor shape of the input. That's important because convolutions are exploiting the spatial locality of the pixels, okay? So we don't flatten it, and we convolve with some filter bank, W, and we get some hidden layer activations. And that's going to be the activation map that we talked about. So we think of this as a bunch of features that are extracted from our image, taken through the relayer. And then we take that and convolve it with a different filter bank, and we get features of features. And then we convolve it again, we get features of features of features. We keep going as long as we'd like. And eventually, we have to get scores out. So, but what we really didn't talk about was connecting, like what happens, like how do we, there's something missing here we haven't talked about. So let's talk about first H2B. What shape of thing is H2B? Is it a scalar, is it a vector? Like, what is it? It's tensor, okay? How big is it? Smaller than our image, somebody said. True. Okay, so yeah, you can't tell from the pseudocode exactly, but if we make some assumptions like our filters are 3x3 filters, and we have 2 layers here, then this is going to be roughly like 30 by 30 by however many filters we have. Okay, but then how do we get from that to scores?
Flatten it.
Oh, okay, yeah. Well, we can just do the same thing that we've done before. We can just take H2B and, wait, stand by. There we go. And flatten it to whatever shape it needs to be. I just put some numbers there. Flatten it to whatever shape it needs to be, and then essentially have a fully connected layer at the end. So you see, this is a very common topology design paradigm in machine learning. So you go a bunch of convolutions, but then you got to get the shape of that thing right, and so you reshape it and put it through a couple of fully connected layers. Okay, so hopefully that ties together a little bit about where we've been so far. Let me ask you this, how many parameters do we have in this model now, roughly? Estimate a few things. Let's suppose, you can't quite tell. Tell me how you calculate it. Let's suppose the first bank, there's like 64 filters in the first bank, and then I suppose there are 3x3 filters. 64 times, and how many parameters are in one 3x3 filter? 27.
27, because it's 3 by 3.
Because it's RGB image. So X flat is a 32 by 32 by 3. So the filters are 3 by 3 by 3. So there'll be like 64 times 27. So how many parameters is that, roughly? Yeah. So like way smaller, like orders of magnitude fewer parameters. And you might be wondering, like, that seems strictly less powerful. In our previous model, which is also only like 4 or 5 lines of code, we had millions of parameters. Here we've only got thousands of parameters. So why do convolutions even work? So today I'd like to continue our discussion of convolutions and sort of begin to develop some intuition about why convolutions work. Go ahead.
In the process, could you maybe explain other applications where convolutions are used? Because in the context of images, that seems super intuitive. You know, you have data that goes around, but for like text processing or that type of thing, how does it apply?
Yeah, okay, so great question. The question was, when, besides images, are convolutions useful? And the answer is, anytime that you have locality between inputs. So if I give you, for example, an audio sequence, a little frame of audio, you could imagine running one-dimensional convolutions across that audio. You could also imagine giving a spectrogram where there's correlations in time and frequency, and you could imagine two-dimensional convolutions running across that. You can also do it with text. So in fact, it turns out that some of the most recent neural machine translation stuff that we'll see later in the semester does a convolutional approach to text processing. And that's because there's correlations between, there's like a sequencing, a temporal sequencing across words. And so you can imagine running essentially feature detectors across the sentence and extracting features and then features of features and then features of features of features. Times that it's not appropriate are times when you just have a bag of data and there's no particular reason to sequence it in one way or another. And it sort of depends on what your application is, what that might be.
Perfect. Thanks.
Okay? Yeah, convolutions tie parameters together, so it dramatically reduces the number of parameters, but the reason that it can do that is because of essentially invariances or correlations across the input dimensions. Yes?
Is it ever common to use time as another dimension of image convolution?
Yeah, totally. So you can totally imagine width by height, by RGB, by time. So you have a 4-dimensional tensor where you have a stack of frames. And you could imagine 3-dimensional convolutions that search for features in both time and space. Totally possible. If you have powerful GPUs. If you don't, that's impossible. Yeah. Okay, good. All right, so let's keep going. So I'd like to, again, just like refresh your mind a little bit about the intuition of what these things learn. So we start off with some image. It goes through a series of convolutions. And the things that are learned are low-level features in the earliest layers of the neural net. So these are things like these little wavelet things. And then higher order features in the middle. And then things like object-y or parts of objects at the very top. And then at the very end, you sort of strap this linear layer or fully connected layer on that's essentially acting as a classifier. And interestingly enough, what I think a lot of people think is kind of cool about this is that the things that emerge, the receptive fields of the neurons that we'll talk about in just a second, that emerge, kind of mimic the human visual system. So just like our lowest level vision, the neurons, they respond to features that are very similar to the features that neural nets respond to. And then as you go deeper and deeper into human cortex, the hierarchy sort of mimics what a DNN looks like. And I think it's a whole lot of interesting research has been done there. Okay, so let's skip a couple of these things. Oh yeah, so, and I think we saw examples like this where we saw, pictorial representation of things that get extracted. But you can sort of see in this particular topology of convolution value, and then a pooling layer, convolution value. So there's 8 layers, or six layers in this neural net, followed by a fully connected at the very end. Okay, so let's briefly talk about a little bit more about how these convolutions work and some of their properties. So remember, we have a little, say, k by something filter. It slides across the image. That gives us an activation map. We take a bunch of these together, and we get an entire filter bank. So let's suppose, I'm going to take a little closer look at spatial dimensions. So let's suppose we have some input, and we have, our input is 7 by 7. We have a 3 by 3 filter. So we slide it across. We calculate the output numbers. So how big is the output going to be?
5.
Anybody? It's okay if you read it. You can just say it.
5 by 5.
5 by 5. Okay, that's right. So 5 by 5. Okay, and when we do that, remember the filter has to fit inside of the image. Now there's another sort of way we can tune these, and that is to introduce what we call a stride. So a stride is where the filter, instead of marching pixel by pixel across the image, skips some pixels. It does just what you think it's doing. It strides. And so a stride of 2 means we start there, and then the next one, we hop 2 pixels over and apply it. And the next one, we hop 2 more pixels over and apply it. Darn, I gotta tweak these slides. Okay, so how big of an output do you get?
3 by 3.
3 by 3. Man, I was like stealing my own thunder. Okay, so you get a 3 by 3 output. Okay, and striding is useful. So striding, when you stride across an image, it reduces the size of the resulting output activation map much, much faster than if you just stride with a stride of 1. Okay, so let's see. So now what happens if we have a stride of 3?
Then you need overlap.
Okay, what happens? Stride of 3.
You fall off the edge.
Did somebody say false? Yeah, so it's a little funny. A stride of 3, you can imagine, okay, first one's there. The second one like moves over 3, but then the third one, it like doesn't fit somehow. Like it doesn't neatly fit inside. So most people would say that in general, you can't apply a stride of 3 to something like 7 by 7 unless you have some sort of padding around the outside. Okay, and so, but in general, you can, and you're going to need to know this for your next lab. So in general, you can calculate the output size of an image as a function of the size of the image, n, and the size of the filter, f, and the stride of the filter. And so here we see that if we had a stride of 3, we plug it into this little equation, so n minus f divided by stride plus 1, we get 2.3, and we're like, okay, yeah. Something weird is going to happen on the boundaries because it doesn't quite fit. Okay, but in practice, remember I say it's common to zero pad. So what I mean by that is we take our input image and we put zeros all the way around. And let's suppose that we have a 7 by 7 input. Yeah, see? All right, I'm not going to advance the slide. We have a 7 by 7 input, a 3 by 3 filter. We convolve it with a stride of 1. It's padded with zeros all around. So what will the output size be? 7 by 7? I think that's what I heard. Yes, 7 by 7. So in general, it's very common to see convolution layers with a stride of 1, filters of size f by f, 0 padded with f minus 1 over 2, 0 padding. And actually, in tools like PyTorch, you don't even need to calculate the amount of padding needed. You just say, hey, PyTorch, convolve this tensor with this filter, and do it in a way that the result is the same size as the input. And it will helpfully calculate all the padding for you. Okay.
So
Yeah,
you can
sure.
pad it with more than just one layer of zeros?
Yes, absolutely. Absolutely.
What if you define a stride that's like pushes it completely off the input initially with one go? Does it give you an error?
Probably.
Okay.
I've never tried that because,
Just like if you accidentally do
yeah, accidentally, yeah, probably. You probably get some crazy Python stack trace. It's totally abstruse. You won't be able to defend it at all. Go ahead.
Does TensorFlow allow you to define which variable or which number the padding is? Which number is used by the padding?
No, because there's very few reasons to use anything other than 0. So there are a couple of other things you can do. Like there's a whole mathematical theory behind convolutions. We're doing something called linear convolution. There's like circular convolution, and depending on how you set things up, padding with zeros at the boundary might not be the right thing to do. And another thing you could do is take the input and mirror it across the boundary. And then that has certain properties when you do the convolution that turns it more into a circular convolution, FFT. And you can avoid some edge effects if you do stuff like that, but most of the time people don't care. And the reason for that is we don't know what any of this means anyway, and so it's perfectly fine to expect the neural net to learn to cope with edge effects. Like we're not trying to do something super mathematically precise in the same way like an FFT where every number means something very specific. Good. Any other questions? So in general, we don't worry about it. We just say, hey, PyTorch, do it, and pad as you see fit, and they'll pad with zeros. It is useful, I think it's useful to know that that's what's going on. So if you have very small things that you're convolving with, the edge effects might be significant. Or if you're using very large filters, the edge effects might be significant. Yeah, questions?
Just story along that note, we've had issues where the network has learned the edge effects, and so it's learned the dependency of things at the edge of the image versus the middle of the image.
Oh, yeah. Oh, cool. Yeah. Way to go, machine learning. That's awesome. So yeah, it's not, I guess maybe it's not fully invariant. Like the network knows there's an edge to the image. Yeah, that's cool. Okay, great. Let's keep going then. Sorry, any other questions to this point? So, okay, really quick review. So remember that if we start with like a 32 by 30 by 2 by 3, we convolve with 6 5 by 5 by 3s. We end up with an output map of 28 by 28 by 6, convolved by 5 by 5 by 6. And remember that the last dimension of the filter has to match the size of the activation map. Keep going like that. Okay, so let's imagine, just a quick quiz here. I have a 32 by 32 by 3 input volume, and I convolve with a 5 by 5 by 5 by 5, 10, 5 by 5 by 3 filters with stride 1 and padding 2. The output volume size will be? Okay, I heard it here. Why don't you talk to your neighbors and see if you can figure it out? You have 15 seconds. Go.
32 minus 5, 7 minus 5 is 27.
Okay.
Divided by
15 seconds are up. What do you got?
It's like 7 by 27 by 3.
Shout it out.
34 by 34.
What?
32 by 32.
27 by 27 by 3? Oh.
Yeah, I don't think you can ever get, you can't ever get something bigger than your volume.
You can.
29 by 29?
Oh, if
You do full padding so that the corner of your kernel.
Oh, yeah.
Yeah.
Okay, if you do that, yeah. Okay, fair enough. You have to read the passage.
It's
Okay.
in the reading.
So what is it for real?
32 by 32.
32 by 32 by 10. Right? Okay, great. Good. You're going to have to answer a bunch of questions about this in your lab. That's why we're going through this. Yeah? Yeah, right? So that's right. So in the very first layer, those three maps happen to be RGB. But after that, who knows what they are? They're just features. Okay? And so there's a nice compositionality here where you can just take one, the output tensor of one layer and plug it into the output into the next one. Okay, and how many parameters do we have in this? And 5 by 5, except they're 5 by 5 by 3. The answer starts with 7 and ends in 150, right? 750, okay. Of course. Oh, +1 for bias. Oh. Okay. Okay, so just a quick summary. That's part of myself. This is awesome. Okay, so to summarize, here's just some like pseudocode to help you calculate and think about the dimensions of convolution layers. So the reason I'm dragging you through this is because as you begin to develop your own topologies, there'll be many times when you'll say, okay, hey, yeah, I've got this layer, it's outputting this, and I want to take this thing and somehow transform it into this shape of thing. And you're going to have to know kind of how to reason about these numbers. So that's why we're going through this. Hopefully this is all pretty clear now and you'll understand all of these numbers, but so you got number of filters, spatial extent, stride, the amount of zero padding are the critical input numbers, and then there's various formulas that you can use to help you calculate the resulting number of parameters and the dimensions and what you need. So, by the way, yeah, almost everything is powers of 2, and the reason for that is just as you begin to stride and reshape and do things, almost always powers of 2 are super helpful. So that's why you see things like data sets that are 32 by 32. Okay, by the way, a 1 by 1 convolution makes perfect sense. So what is a 1 by 1 convolution doing? Think about this for a second. So when I say 1 by 1, that's the size of the filter. So if I have an input tensor of 56 by 64, and I have a 1 by 1 convolution, what is this actual shape? It's 1 by 1 by 64. So it has 64 numbers. What is that learning?
Seems like we're learning the relationship between each of your channels. You have 64 channels, and that 1 by 1 is just taking all 64 of those and merging the channels.
Yes.
Changes
Keep going.
the third dimension, 60.
Keep going.
You can also use
So we're going to take this 1 by 1 by 64. So it's going to have 64 numbers, and we have our input volume, and we're going to take this 1 by 1, and we're going to scan it across each pixel, and we're going to get out. We're mixing. Wait, hold on. I heard some good answers.
You're mixing channels.
Mixing channels. What do you mean by mixing?
So you're applying weights to certain channels and then you're adding them together.
Yeah, right. So we got a 64 by 64 tensor. In this case, 56 by 56. Sorry, 56 by 56 by 64. And we've got a 1 by 1 convolution which has 64 numbers. We're going to apply it to each pixel in this 56 by 56 array. And we're going to dot product it. And that's going to give us one output number. So it's as if we take this 3-dimensional tensor and we're flattening it in the 64 dimension. And so the thing that's being learned is a linear combination of all of your features. And so it's just going to learn how to take your feature map volume and compact it down to a 56 by 56 by 1 image. But then you do it however many times you want to do it. So yeah, go ahead.
This might be a really gross undersimplification, but is this essentially like taking a color image with 3 channels and flattening it into a grayscale image?
That is what it could learn, yes. So if the filter was like 0.3, 0.3, 0.3, it would be almost exactly that. But we can learn any combination, and of course these can be features of features of features that we're learning to combine. Yeah.
So here's an interesting question. You know, in all of these, you tend to have multiple filters. Like there's only 32 separate filters. How do you expect each of those to find different things to?
Good question. Yeah, so if the input is the same, and we have 32 filters, and they all are going to get applied to this, and they're all going to spit out some output, shouldn't the gradient of the parameters with respect to the loss for all of those be the same? And if the gradient's the same for all of them, we take a step in the gradient direction, we're going to update them all in parallel. They'll all be the same numbers, and so they'll always be the same numbers. Is that what you're asking?
Yes and no.
Okay.
So I guess, yeah, that in this specific case. But in the general sense, I mean, we were looking at, you know, all the different cells on the video watch today. Why don't you ever get cells that learn to recognize the same thing?
Why don't you get cells that learn to recognize the same thing?
Is that when you made the loss function?
Yeah, so there's 2 things that are going on. So first of all, it turns out the gradients for all of the cells are a little bit different. The reason is random initialization. So by the way, this is like why random initialization is critical. If you initialize all of your parameters to the same number, then the gradients for all of them will be equal, and they'll all move in lockstep, and they will all learn like one thing. Okay, so that's reason number 1. So slightly different random initial conditions means that everybody gets slightly different gradients, and they just start updating, and they just like go wherever they're going to go, but it will be different places. So that's answer number 1. But the second half of your answer, okay, so let's assume that gradients have broken, or random initialization has broken the tie. Why do they end up like in different places? What do you think?
Because it's more beneficial?
Yeah, it's an emergent property of minimizing the loss function. You get a better loss if they learn different things. And so we are like relying super heavily on the optimizer to do its job. Right? It's the optimizer that, and this magic of gradients, that's saying, if I want to get to the very best part of this error surface, of this loss function surface, the place I'm going to end up using my resources sort of optimally will mean extracting different features. Or maybe said another way. Yeah, no, I think that's the answer. Okay, good. Great question. So why 3x3? So I've talked about 3x3 filters, 5x5 filters, but you might be thinking, Dr. Wingate, why don't we use like 128 by 148 filters? That'd be awesome. Here's why. You can do that, of course. But it turns out there's some really good reasons not to, and nobody who's doing state-of-the-art research uses anything bigger than about a 5x5 filter. So almost always super, super small. So you might say, why? Okay, well here's a little bit of intuition that I'd like to build in your head. So people think of this as called the power of small convolutions. So let's imagine we have 2 3x3 convolution layers, stripe 1. So we have some input image, and let's imagine the output activation map here, the first convolution, the results of the first convolution layer. This pixel in the middle, which pixels did this guy in the middle rely on when we computed this number? Yeah, these ones right here. That makes sense to everybody? Like we had this little 3x3 thing, and as we scanned it around, in order to calculate this number, we needed these 9 numbers. But now let's consider a pixel in the middle of the second convolution layer. Which pixels did it depend on in the first convolution layer? The red ones, right here. But which pixels did it depend on in the input layer?
All of them.
All of them. Okay, so how big of a region in the input does a single neuron and the middle neuron in the second layer sees all of them? So what is the effective, this is called the receptive field. What is the effective size of the receptive field of a neuron in the second convolution layer? 5 by 5. So so in other words, two 3x3 filters stacked together gives us something kind of equivalent to a 5x5 filter. Just we've traded depth for filter size. And so if we stack 3 convolution layers, how big of an input region does a neuron in the third convolution layer see?
7 by 7.
7 by 7, okay, right? Because a pixel, say here, depends on this 9 by 9, but this thing out here depends on that 9 by 9, but that guy out there depends on that 9 by 9, and so the answer is a 7 by 7 region. So 3 by 3 convolutions gives us approximately the same receptive field, at least, as a single 7 by 7 convolution. Yes?
So if you go back 2 slides to the one where you have the 3. So you said that one depends on all of them.
Yes.
Why is that? Oh, because of the thing we talked about.
Yeah, so if we twiddle this number here, then it's going to twiddle this number here. And if we twiddle that number there, it's going to twiddle that number there.
Okay.
Right? That's what I mean.
Is that why filters tend to be odd as well, because they have a center?
Yes. Okay, good. So now let's just think a lot about properties of stacks of small filters. So let's suppose we contrast one 7 by 7 convolution with a stack of 3 by 3 convolutions. First of all, let's compare the number of weights. So how many weights do you have in a 7 by 7? And let's just assume that the input tensor dimension is like 1, just to make things easy. 7 by 7, so how many weights do we have?
49.
49. How many do we have here?
27.
Right. And if we were to, 27, right? 3 times 3 times 3. And if we were to add the number of channels, we would see that we need 49 times c squared. C is the number of input channels. Whereas here we only need 27 c squared. So there's fewer parameters, but similar receptive fields. And we say that there's more nonlinearity when we stack 3 of these together than if we stack a single one. And so I think in general, fewer parameters but more nonlinearity, that's a good thing for us. We want highly nonlinear function approximators, and we want to be parsimonious with the number of parameters. By the way, this translates directly to computational efficiency. So I think we're running low on time, so we won't do this, but you can sort of imagine that sort of the number of multiply adds that you're going to do is essentially proportional to the number of parameters. And so it turns out that a stack of small convolutions gives us also less compute, but more nonlinear. It's another good thing. So this is why state of the art is lots and lots and lots of small stacked convolutions, 3 by 3 convolutions. Okay, we have 3 minutes left for class. Yeah. So I was going to segue into something called getting things to work. Since you're going to be, so for your lab 3, you're going to be starting to build your first deep neural net. Very exciting day for you. And there's just a few rules of thumb as you begin to do this. Here's a couple rules. Let's go through these. Number 1, use the atom optimizer. We haven't gotten there yet. Just trust me for an F. Number 2, use ReLU. We've talked about why. Number 3, do not use an activation function at your output layer. Okay, what do I mean by that? So when we calculate scores, I'm saying don't use an activation layer. So I think like in our little model here, notice that everything else go convolve, ReLU, convolve, ReLU. But at the very end, you do dot product, but there's no ReLU. Why not?
It's wasted computation.
Waste of computation? I don't know, it's more nonlinearity.
You lose information or get a range that you don't want.
You get a range you don't want is actually the big reason. So if your scores can only be positive numbers, then that's a little bit funny. There's no particular reason at this point. Like, hopefully the rest of the network is taking care of the nonlinearity that we need. Yeah, you don't want only positive scores. You want there to be negative scores.
But you would consider softmax would be an activation function.
Yeah, oddly enough. That's correct. Softmax is not considered an activation function, even though the result is mostly positive things. Okay, good. I think we're out of time. Okay, well, that was too bad, because that was really good stuff that you're going to miss. Let's see, is there any other rules we can talk about? I don't think we have time. Okay, well, have a great day, and we'll pick this back up again on Wednesday.